So last section we're going to look at this week is 3.3. As I said, we'll spend today and tomorrow kind of learning the material, and then Thursday will be a review, and Friday will be our test on these two sections. I think there's about 16 questions on the test, and 10 of them are going to be on area of a triangle. I think close to 10 of them. So the majority of the test will be on what we learned yesterday. All right, so section 3.3 is on what we call trig identities. So let's just first look at what is an identity. Okay, maybe not even a trig identity, just maybe an identity from algebra. And then we'll look at an identity in trig. So let's say we had two functions, okay, or two formulas. A lot of times we will name them like f of x and g of x. Just two different equations. Two functions are considered equal. I'm going to show you an example. Are considered equal to each other if whatever value you pick and plug into f, if you pick that value and plug it into g, you always get the same answer. Always. So let's say somebody in the class had a formula for f, somebody else in the class made up another formula and they called it g. If I can plug a number into formula f and I can plug that number into formula g and I get the same answer every time, no matter what number I plug in, then that's an identity. Right, let me show you an example. Here's an example of two functions. The top one is f, the bottom one is g. Formula f equals 4x plus 8, and formula g equals 2 times 2x plus 4. Now they don't look identical. Okay? If I showed that to somebody in first grade and said, do these two things look exactly the same? They'd say, no, they look different. Right? But let's try plugging in a number for x and see what happens. Ben, can you give me a number? 3. Let's plug 3 in to this formula f. What's 4 times 3?
Well,
plus 8? 20. So if you plug 3 into the top formula, you get 20. Let's plug 3 into the bottom formula. Vivian, what's 2 times 3?
6.
What's 6 plus 4?
10.
And what's 10 times 2? 20. Same answer. We got 20 when we plugged it into the top. We got 20 when we plugged it into the bottom. It didn't matter what number Ben picked. He could have picked 3, 4, 12, negative 18. No matter what he picked, if we plugged it into the top and plugged it into the bottom, we would get the same thing. Right? So these are exactly the same equation. Any question on that idea? Right, and that's called an identity. Two things that are exactly the same. Even though they look a little different, there might be a way to simplify one of them to make it look like the other one. And that's what we're going to be doing with trig identities. We're going to have two things. They might look a little bit different, but there's going to be a way to simplify one of them to make it look like the other. Okay. So an identity is an equation that is true no matter what values are chosen for the variables. Okay. Another example of something that's kind of like an identity is Pythagorean Theorem. That theorem doesn't just work for certain numbers. Okay? That theorem, if you're dealing with a right triangle, it works all of the time. It's not like you can only use Pythagorean Theorem if a side is 4 and the other side is 6. You can use Pythagorean Theorem for any numbers if you're dealing with a right triangle. So that's a formula that works no matter what values you plug into it. Plug in any two and you can solve for the third. All right. So first thing I'm going to do is show you guys different groups of identities. Okay, we're going to have certain, we'll call them like our fundamental identities, kind of the basic ones that we're going to use to do the problems today. So the first group of identities that we're going to look at are called reciprocal identities. And we've already done these before. What does reciprocal mean? Hey?
Like opposite, or like kind of opposite, but not really. It's
Like-
like the same thing, but it's just inverse.
So like 5 and -5?
Well, -5 over 1. Is that right? Because in a fraction, the reciprocals are
So can you do that again? It's like what?
like,
So what does that mean?
you just flip
You
it.
flip it. Yeah, you flip it. So reciprocal is when you, right? It's when you flip it. So we've already seen identities where we've had to flip them. For example, when we take the sine and we flip it, it gives us the cosecant. That's called a reciprocal identity. And it's an identity because it works all of the time. It's not like you can only find the cosecant of 10 degrees or 12 degrees or 13. No, you can find the cosecant of any angle you want by taking that angle and flipping the sine value. Any angle. It's always true. How about the secant? Anybody remember what trig function do you have to flip to calculate the secant? Yeah.
Cosine?
Yep, you flip the cosine. And that's not just true for certain angles of theta, that's true for any angle. If you take any angle, take the cosine of it and flip it, it will always give you the secant. And how about the cotangent? Anyone remember the trig function we have to flip to get that one? Yep, the tangent. So those are the three basic reciprocal identities. Now, we can take this and we can rewrite it, but it's still the same identity. Let's look at something that's a little simpler before I rewrite it. We talked about that formula at some point. I think we mentioned distance equals rate times time, or it's a formula you see in different places. Now, what if I wanted to get r by itself? What would I have to do on both sides? Yep.
Divide by t.
Divide by t. Distance divided by time equals rate. Okay. What if I wanted to get t by itself? Yep.
Divide by r.
I could divide by r. That's not three different formulas. That's just taking the same formula and rewriting it different ways. Okay? We can do exactly the same thing with what we have on the other page. Now, look at the pattern here. You can always switch what's in the bottom and what's on the other side, and it'll give you another version of the same formula. If you switch the r and the t, you get d divided by r equals t, which is another version of the same formula. So, let's see. Let's apply that same idea here. You can always switch what's on the bottom and what's on the other side and get another version of the same formula. So I could rewrite that top one like this. Sine equals 1 over cosecant. And all this is really saying is if you flip the sine, you get the cosecant. If you flip the cosecant, you get the sine. How about the next one? Anyone have an idea how I could rewrite the second one on the left? Pete?
Cosine of theta is 1 over secant.
Yeah. So the one on the left says if you take the cosine and flip it, you get the secant. If you take the secant and flip it, you go back to the cosine. Again, we're kind of repeating ourselves when we write these ones on the right. They're really repeats of the one on the left. Right? They're not really different. But I'm just writing them. And how about this last one? Anyone have an idea what this last one would be? Aiden?
Tangent of theta is equal to 1 over the cotangent of theta.
Yeah, exactly. Again, really a repeat of the one that's on the left, but if you take the tangent and flip it, you get the cotangent. If you take the cotangent and flip it, you go back to tangent. And those are called reciprocal identities. So that's one of the groups we're going to look at. There's 3 main groups. Okay, today we're going to do 2 of them. Tomorrow we'll do the 3rd one. The second group we're going to look at is quotient identities. And before I show you this one, I want to just go back to something we've done before. When we did unit circle trig, we had formulas for sine, cosine, and tangent. I'm not talking about like opposite over the hypotenuse, adjacent over hypotenuse. It was all based on a coordinate. Does anybody remember when we did unit circle trig, what letter sine was equal to? Yep.
Y.
Sine was equal to our y. How about cosine? Anyone remember what that one was equal to? Yep. Yep. Cosine was x. And how about the tangent? It used both the y and the x. Yep.
Y over
It was y over x. Those are formulas we had before. But look at what you just wrote right here, or what I wrote. Y over x. Raymond, what did we just say up above that y is equal to?
The sine.
Sine. And what did we say up above that x was equal to?
Cosine.
Cosine. So what this really means is that tangent is the sine divided by the cosine. That's a quotient identity. To calculate tangent, you can always take the sine and divide by the cosine. Now the point is not really to do this with numbers. I'll show you an example with numbers. Well, let's say you wanted the tangent of 10. And your tangent button didn't work. Well, you don't have a tangent button. Well, instead of taking the tangent of 10, let's say you couldn't do that, you could do the sine of 10 and divide by the cosine of 10. And you get exactly the same thing. So technically, you don't need tangent. You can do everything without it. It's a little bit more work to type it in, but you absolutely do not need tangent. You can do everything in trig without it. In fact, you can do everything in trig with just sine. You don't need tangent, you don't need cosine, you don't need secant, cosecant, or cotangent. You could do everything with just sine. But that's kind of like saying you could wash your car with a toothbrush. You could. But sometimes it helps to have some other things to make it a little easier. And that's why we have the other trig functions. All right. So tangent is sine over cosine. Anyone have a guess what cotangent is? Yep.
X over y?
It's x over y, which would be what over what?
Cosine over sine.
It's cosine over sine. Okay, and those are called the quotient identities. And that's the only two. All right, so let's take a look at one of these reciprocal identities. Let's take a look at sine equals 1 over cosecant. Let me copy that in. let's look at this. This means sine squared. It means sine to the second power. You might wonder, well, why don't they just put the second power like this? Well, you can. It means the same thing. But a lot of times when you want to raise a trig function to a power, they put the exponent right in the middle. This is how they do it. But anyway, my point is, what does something to the second power mean? Like if you had to write this out without an exponent of 2, what does it mean? Yeah, can you do that? Yeah, it means sine theta times sine theta. Any question on that? All right, so now let's take that kind of one more step. And let's do this. Let's say I wanted to figure out that. Can someone remind me again, which trig function do you flip to get, well, cosecant? Yeah?
The cosine?
If we flip the cosine, that's going to give me the secant. Which trig function do I flip to get cosecant? Yeah? Sine. Okay, that's what we just wrote on the other page. So now, what do you think I would do to get cosecant squared? If we're not sure, let's break it down. What does cosecant squared mean? If we just wrote it without an exponent of 2. Yep.
Cosecant theta times cosecant theta.
It means cosecant theta times cosecant theta. Now look up above. What trig function do you flip to get cosecant? Yep.
Sine.
You flip the sine. So to get the first one, you would flip the sine. And to get the second one, you would flip the sine. So it's 1 over sine times another 1 over sine. Now multiply straight across. 1 times 1 gives me how much? 1. Now sine times sine is just like doing x times x. What do you think sine times sine is? Yep.
Like sine squared or 2 sine?
Sine squared. So we started with that, and we got that. Right. Let's try one more to see if we see the pattern. Hopefully we don't have to do it all out like that. What if I asked you for that one? How do you think you would get cosecant cubed? Yeah?
Just multiply it 3 times.
So what would be in that box?
Oh, sine wait, cube?
Where would the
1
sine
over
cube?
sine cube theta?
1 over sine cubed theta, yes. So what I'm trying to show you here is these identities that I showed you, they work with higher exponents. In general, you're never going to have to work with an exponent higher than a 2. But you can use, and here's another example, you can use the reciprocal and the quotient identities with higher powers. Right? If tangent is sine over cosine, then tangent squared is sine squared over cosine squared. Tangent cubed would be sine cubed over cosine cubed. Right? So you can use the identities with higher powers. Here's another one. I think we did that one. Cosecant squared is 1 over sine squared. Again, the higher powers doesn't come up a lot. But what you really want to make sure you know is at least the basic case. This is like when they're all to the first power. You can pretend like there's a 1 here, a 1 here, and a 1 here. But that number could be anything. It could be a 2, and a 2, or a 3, and a 3. Again, we don't go much higher than 2. All right, so let's look at an example. So this is the kind of problem you would see about a trig identity. Kind of like the algebraic identity I showed you at the beginning. We had two things that looked different. But when we plugged the number in that Ben gave me, they really were the same. We've got something here that can be simplified, and when we're done, it's going to look a little bit more compact than what we started with. And there's several tricks we can use to simplify a trig identity, and one of them is to change everything in the problem that isn't a sine or a cosine into a sine or a cosine. And the way we can do that is using the two groups of identities I gave you earlier, the reciprocal and the quotient. Now for this one, if we already have something that's a sine or a cosine, we're just going to leave it. If it's not, we'll change it. So let's start with secant. How can I rewrite secant in terms of sine or cosine? What does secant equal? Yep.
You can do 1 over cosine theta.
It's 1 over the cosine. So we have 1 over cosine times, let's leave the other one alone because it already is cosine. So if it already is a cosine, we're not going to change it. Any question about why secant is 1 over cosine? If you're not sure where we get that from, right there. Secant is 1 over cosine. All right. Now, cosine isn't a fraction, but how about, Autumn, how could I make cosine a fraction?
Put a 1 under it.
Yeah, we could just put a 1 under it. Now, we're going to multiply those two things together. What's going to happen even before I multiply? Anybody see something here that simplifies? Jacob?
They all simplify together, so that's just 0.
So what if you had, this is the same problem basically. What would you do there before you multiply?
Simplify 3.
Okay, and if you simplify, can you tell me how? Anyone else tell me what's going to happen?
Simplify.
Okay, so how do I do that? Pete?
I think you just multiply. 1 times 3 is 3, 2 times 1 is 3, 3 over 3 is 1.
Okay, so you just would multiply straight across?
If that's what I'm supposed to do.
It's an option. You're going to have to reduce.
Or I could just do 1 and do it diagonal-wise.
So you could reduce first or you could reduce later. We have to pick. We're going to have to reduce here. Either now or later. Let's do it now. Okay. When you have the same factor in the top and the bottom of a fraction and you're multiplying, what happens? Ben?
It becomes 1.
It becomes 1. It cancels out. Right? 3 goes into itself once. 3 goes into itself once. So all you end up with is 1 over 1, which is just 1. How about on this one? What would cancel out when I multiply straight across? Vivian?
Cosine.
The cosine. Okay. So all the rules we can use that we simplify fractions when we just have numbers, they're all going to apply for this as well. If you have the same thing in the top and the bottom and you're multiplying, not adding or subtracting, that's different. But as long as you're multiplying between the two fractions, and you have the same thing in the top and the bottom, it cancels out. So all we're left with is 1. So that's an example of a trig identity that completely simplified down to a single number. All right, let's try another one. So this one is cotangent divided by cosecant. Now, what trick did I use last time to start the problem off? What was the trick that I wrote in the notes? About Katrina? What was the trick that I wrote down in the notes?
No idea.
Did you write it down?
Which one?
I think I called it one trick. I think I said trick. A trick to simplify trig expressions. What's that?
You gotta change it to Sine Equals.
Yeah, let's change everything to sines and cosines. Okay, so that's one trick that you can use to do these problems. So let's try that here and see what happens. Okay. What is cotangent? If you rewrite it in terms of sines and cosines. So actually we have two formulas for cotangent. I want the one that has sines and cosines. Yep.
Sine over cosine?
That would be tangent.
Cosine over sine?
Cosine over sine. Cosine over sine. And what about cosecant? How can we rewrite that one? Pete?
Pass.
Anyone help them out? How do we rewrite cosecant? It's going to be one of those 8 formulas we have. It's got to be one of them. Yep.
1 over cosine.
1 over cosine would be SEC. But you're on the right idea. Yep.
1 over sine.
It's 1 over sine. Okay. Now, we have to divide those two fractions. We do that the same way you would divide numbers. And we're going to hope that something cancels out or something good happens. So how do we divide two fractions?
No, I wrote that.
That's all right. So what do you do when you have to divide two fractions? Yeah.
Multiply by the reciprocal.
Okay, so go ahead and tell me what would I have? What times what?
Cosine over sine times sine over 1?
Yep. Cosine over sine. So when you have to divide two fractions, you keep the top the same. And you multiply by the reciprocal. So sine over 1. All right. Now, what's going to happen when you multiply those two fractions together? Yep, Ava.
The sine is gonna cancel out.
Sines are going to cancel out. And what are you left with?
Just cosine.
Yeah, cosine over 1. We don't need to write over 1. It's just cosine. So the cotangent divided by the cosecant simplifies down to just the cosine. And where we don't do the application beyond this is kind of where we stop. But the next step would be, if you were doing something in calculus, this is complicated to work with, the original problem. It's two different trig functions and it has division. We took something that was complicated and we turned it into a single trig function, there's no division at all. That's much, much easier to work with, and it's exactly the same thing as what we started with. It's just simpler. But again, we stop with cosine. We don't do the next step, which would be calculus. All right, let's try this one. Again, I had to do something with that. That's a little complicated because I have two different trig functions and they're being multiplied together. It would be nice if I could simplify that down to one trig function. Sometimes I can, sometimes I can't. Depends on the problem. Usually the ones I give you are going to simplify down a little bit. So Aiden, what would be the trick I want to try here? The only trick we know so far.
It'd be the sine and cosine.
Exactly. Change it to sines and cosines. That's not the only trick. There's other tricks, but that's the one we're looking at right now. All right, let's start with cosecant. Angie, how do I rewrite cosecant?
1 over sine.
Perfect. Yep. Cosecant is 1 over sine. How about tangent? What is tangent? Yep.
1 over cotangent?
You can write it as 1 over cotangent, but I want to do the trick that Aiden said, which is change it to sines and cosines. Not saying we won't ever use that one, but not for this problem. Yep.
Would it be sine over cosine?
It would be sine over cosine. And if you've done that step right, the goal is that hopefully something is going to cancel out. Is there anything that cancels out there when we multiply? Yep. Sine theta. And what are you left with?
Oh, 1 over the cosine theta.
Yep. You're left with 1 over the cosine. And it's kind of a matter of opinion. How, can we do anything else with that? Technically, we could get rid of the fraction. When you flip the cosine, which trig function does that give you? Yeah? The secant. So, is that any more simpler than that? I don't know. I would say it is because now it doesn't have a fraction. So we started out with two trig functions that were being multiplied, and we turned the whole problem into just one single trig function. So this is a much simpler way of saying what we started with. And that's what we're trying to do, find the simplest way we can write the problem. Okay, questions on that? Yeah.
So on a test, you would want us to end with something like secant or cosine?
We won't always end with just a single trig function like the first problem we did. We ended with a single number. That can happen. Usually you don't end up with a number, but sometimes you do. But everything I've circled is what you'd be ending up with. Okay, that's the answer I'd be looking for on the test. Let's see. All right, let's try this one. So, how come changing to sines and cosines wouldn't work here? Any thought why changing to sines and cosines wouldn't work?
There already is cosine.
It already is sines and cosines. So if it's already sine and cosine, changing to sine and cosine, not really going to help me much. So what do they say to try? They said a trick here is to multiply the top and the bottom by the conjugate. Okay, that's something we've seen before. We multiplied by conjugates when we had complex numbers, and we had an I in the bottom. So remember, the conjugate is when you change the sign of what's in the middle of the problem. So like x plus 2, the conjugate is x minus 2. So he said a trick here is to multiply the top and the bottom by the conjugate of what's in the bottom. All right, let's try it and see what happens. There will be some problems where I give you a hint on the test, and I say, try this. Then there'll be some other problems where I don't. All right, so we'll multiply the top and the bottom by the conjugate. Okay, let's see what happens. Okay, bottom is 1 minus cosine theta. What do you think the conjugate of the bottom is? Instead of 1 minus cosine theta, we're going to have yep.
1 minus 1 over secant.
So we want to leave everything as sine and cosine.
Oh.
So we don't want to change it from cosine. We're going to leave that. Remember, we're just going to use the conjugate. Yep.
1 plus cosine.
1 plus cosine. Remember, the conjugate is when you change the sign of what's in the middle. So in this case, it's 1 minus cosine. Let's multiply by 1 plus cosine. And same thing on the top. Now, top, I'm not going to do that out. And this is the part with identities that gets a little tricky. Why wouldn't you just do it out? Well, I'm not going to do it out because I know something is going to completely disappear in the next step. So that's why sometimes when I teach identities, I try to explain it like if you play chess, you might do something now that's going to help you 3 moves later. That's kind of how identities are sometimes. And the only way you get better at it is the more you practice, you start to see certain patterns. So I see something that's going to happen here. You wouldn't see it right away because it's your first time seeing a problem like this. But hopefully when you see another one like this next time, you remember this one and you're like, oh yeah, wait a minute. You said not to do that out because something's going to happen. So just watch what happens. Let's leave the top exactly the way it is. 1 minus cosine squared times 1 plus cosine. Now the bottom, I do want to do that out. And when I do it out, we have to FOIL. Okay, that's how, it's just like basically multiplying 1 minus x times 1 plus x. If you could multiply these two together, then you can multiply the two above. It's exactly the same steps. All right. Let's start with 1 times 1. James, 1 times 1 is going to give me how much? 1. Ben, what's 1 times cosine? Cosine. What's 1 times negative cosine?
Negative cosine.
And what happens when you have a positive cosine and a negative cosine? They cancel out, and that's what I knew was going to happen. 1 times cosine is cosine. 1 times negative cosine is negative cosine. Those cancel each other out. And now the last part. Raymond, what's a negative times a positive?
Negative.
Be a negative. And what's cosine times cosine? Cosine squared. Bless you.
Thank you.
Now, does anybody see something that's going to happen in that fraction? And it's the same kind of thing that's happened in the last couple problems. Going to try to make it bigger, but I cannot do that. What's going to cancel out here?
1 minus cosine squared.
Yeah, and that's what I saw was going to happen 2 steps ago. I knew when I FOILed the bottom out that I was going to end up with exactly the same thing I had in the top. 1 minus cosine squared in the bottom, 1 minus cosine squared in the top. And all I'm left with now is 1 plus cosine. And that's it. There's nothing else you can really do with that. It's a trig function that's already written as a sine or a cosine, doesn't have any exponents on it, and it just has a plus 1. How much are you going to simplify a plus 1? You can't really do anything with it. So we started out with a fraction that had two different trig functions, one of them squared, one of them not, and we ended up with something, I think, a lot simpler. No fraction, single trig function with just a plus 1 at the beginning. So that's a pattern to look for. When you see exponents of 2, a lot of times the conjugate is going to help you out. Let's see. Skip that one. All right, let's try this one. Now, this one, I recognize something special about this and something special about that. Now, I know I said we usually change it to sine and cosine. Just like when you play chess, there might be certain moves you usually would do. But every now and then you might do something a little different depending on the situation. What is sine over cosine? Yeah, that's tangent. I'm using x. You can use x, you can use theta. It doesn't really matter. That's just a variable. That's tangent. What's 1 over cotangent? Yeah, that's also tangent. And what do you get if you add a tangent to another tangent? Not multiplying them. If you multiply them, it would be tangent squared. That's different. But what's tangent plus tangent? Just like doing x plus x. Yep.
2 tangent.
2 tangent. Done. See, that's the frustrating part about an identity. Is sometimes you might try all kinds of things, and you start going down this path where it's just getting worse and worse. But if you had thought of the right thing right away, you could have done the problem in like 10 seconds. Right? And that's the thing about identities, that after you practice them, you start to recognize, wait a minute, I've seen that before, and I tried this, and it worked. So you start to recognize things that'll work. And that's it. That's as simple as you can get. That's tangent, so you have 2 tangent. Let's see if I've got another one. Let's try one more. All right. So this is probably one of the harder ones we'll do today. I think it's the last one. We have 2 fractions with different denominators. Anytime you see fractions with different denominators, you should try and add them together first. Because a lot of times if you do that, something will cancel out. Okay, so the trick here is to write it with a common denominator. And that's going to be the last trick for today. So one trick we had was change to sines and cosines. Another trick was multiply by the conjugate. And the third trick is write with a common denominator. Now, if people copy down that trick, I'm going to erase that because I need a little bit of space to do some work. So the easiest way to get a common denominator is just take the 2 denominators that you have and multiply them together. Just like if you had this. And I said to you, what's the common denominator? You could use 35. And if you wanted to add those together, the way you'd get 35 in each denominator, you'd have to multiply the fraction on the left by 7 over 7, and the fraction on the right by 5 over 5. And then you could add Now you have a common denominator. We're going to do exactly the same thing up there. All right, so the common denominator is going to be sine times cosine. What is the denominator on the left missing so that it has the common denominator? Yeah,
Cosine.
it's missing cosine. So let's take and multiply bottom and top by cosine. All right, now let's look at this one. What is the fraction on the right missing so that it has the common denominator of sine times cosine? Yep, it's missing sine. So we're going to multiply by sine over sine. All right, so let's do that out and see what happens. This cosine is on the outside. You want to do it just like that. Okay. All right. How about Lacey? What's cosine times 1?
Cosine.
Cosine. And then cosine times sine. There's nothing we can do with that, but I'm hoping later on I end up with a negative cosine times sine. That will cancel it out. And we'll see what happens. So I have cosine times sine plus, and now do the same thing here. We have cotangent times sine. Let's just leave it just like that for now. Cotangent times sine. Negative cosine times sine. Cosine times sine. Now, is there anything in the top of the fraction that cancels out? Anybody see anything that's opposites? Yeah.
Cosine and negative cosine.
So the cosine times the what?
And the negative is theta. And negative.
Okay, and remember, when you're multiplied, this whole thing is stuck together. These are like best friends. You can't break them up.
Oh, and the other side.
Yeah, so we have a cosine times sine, and we have a negative cosine times sine. That's like having a 3 and a minus 3. When you combine them together, what do you get? 0. You have the positive version of something, you have the negative version of that same thing. So all of that just disappeared. That's 4 things that just went away. Now, let's write down what we have left. Cotangent times sine over sine times cosine. Now, look at what you have left there. Does anybody see something else that would cancel out? Yep.
To get rid of the sine,
We can get rid of the sign. If you had addition there, you can't do that. But it's all multiplication. This is like having 5 times 3 over 3 times 4. You have different things on that diagonal there, but you have the same things on that other diagonal. They cancel out. So we canceled out 4 things, we just canceled out 2 more things. Now we have cotangent over sine. We had a problem like that earlier. What do you think we want to do with cotangent? Yep.
Wait, isn't it cotangent over?
Cosine, yes. Thanks. we cancel these out. That's important. What do you think we want to do with cotangent? Yeah.
Would you want to make it cosine over sine?
Yeah, we could try making it cosine over sine. I don't know if it's going to simplify anymore. If we do that and it looks worse, then we'll say forget it and we'll just stick with that as our answer. But let's try making it cosine over sine and see if something else cancels out. So cosine over sine. And the bottom, we could just write it as cosine over 1, because it's not a fraction. And what did we say we do when we have to divide a fraction by a fraction? Actually, I think this was a good idea. I think something else is going to cancel out. When you have to divide two fractions, what do? 8?
First fraction.
I'll give you a hint. Something times something.
Well, times division of the first fraction by the second fraction.
Not quite. Then
What did you do the top times the reciprocal?
the top times the reciprocal. So now flip the bottom and watch what happens. Now what happens there? James?
The cosines cancel.
The cosines cancel. And what do I have now? 1 over sine, which is? What's 1 over sine? Take the sine and flip it. What do you get? Yeah. Yeah. Cosecant. So that was definitely the hardest one, but look at what we started with. We started with this mess of two different fractions with 1, 2, 3, 4 trig functions, and that whole problem simplified down to just cosecant. Now, to do one like that on your own, it takes a little bit of practice. That's a hard one. Okay? But I'm hoping, like some of the ones in the homework, you'd be able to do one like that pretty quick. Maybe one like that, one like that. Those are the quicker ones. All right, so homework tonight is a worksheet. Okay, it's on Schoology. Okay, so it's 3.3 Part 1 worksheet. I want to say there's like 13, maybe 13 or 14 questions. Then don't get discouraged if you get stuck with an identity. We'll go through every one we need to talk. So don't get too discouraged. It's a tough topic.